Hello dear students, I welcome you to lecture 2 of unit 1st integers and divisibility of mathematics paper 2nd. In last lecture we study the set of integer has an order property or set of integer is a order set, that is if a and b are any two integers, then either a is equal to b or a less than b or a greater than b. This property of integers is called the order property. Also we see that the division by every non-zero integer is not always possible within set of integer z, and between every pair of distinct integers there need not be an integer. These are some properties of integers which are studied in last lecture. In today's lecture we study well ordering principle and Archimedian property. So we start our lectures with definition of the least element. Definition: let us be any order set an element L of S is said to be least element of S if it holds following properties. First property is L belongs to S. This element small l belongs to set S. Second property, this L is less equal x for all x in set S. This L is less than or equal to all element x in S. If these two properties satisfied by our element L, then we say that this L is an least element. From the definition, one can see that or that the least element whenever exists is unique. Hence we call it Examples: first, consider the set S which is an open interval 0 to 1, which includes all real number x such that 0 is less than x is less than 1. 0, x is in between 0 and 1. 0 satisfies the condition second about definition. 0 is less equal to x for all x belong to S, but 0 is not belong to our set S. That is, first condition of definition cannot be satisfied, cannot hold. That is, condition first cannot hold. Therefore, 0 cannot be the element in fact S has no element. Why? If you think if 0 is not a least element, then 0.1 is the least element. But if you take 0.1, then one may think about 0.01. If 0.01 is least element, then one can also think about 0.001, and this set is, I think, infinite set. So now think about 0.0001. Hence, this set S has no least element. Okay, this set, in fact, S has no least element. Okay. Second, S dash is equal to set of x belong to Q set of rationals such that root 2 is less equal x. Now we have to check that this set H dash has least element or not. H dash is the set of all rational numbers greater equal, okay, root 2 is less equal x, means h dash is the set of all rational numbers which are greater equal root 2. Since root 2 is an irrational number, that is root 2 is not a rational number. Therefore, root 2 is not belong to set h dash. Hence, root 2 cannot be least element of h dash. One can do that. Dash has no least element. Next example. Set of integer set itself has no least element. Our set of integer has no least element. So far we have considered example of the sets which did not have the least element. Observe that none of these sets were subset of natural number n. This is not a mere coincidence. We cannot find a non-empty subset of n without the least element. This fact is established in the following property, which is known as well ordering property of natural numbers. So we start our property. Well ordering property of natural numbers. Here every non-empty subset of n has the least element which means that given any non-empty set subset of n subset S of n exists a positive element is positive integer L such that first L belongs to set S, second it is less equal to X in S. This is the property of least element. This is called the well ordering principle. We may also say that the set N is well ordered. This principle can be extended to the set of all non-negative integers by merely including 0 is in it, and thus one may have the well ordering property of non-negative integers. However, we will restrict ourselves to natural number, the set of natural numbers only. Using this principle, we will prove that 1 is the smallest positive integer in the set of natural number. Okay, now we prove one theorem. Proposition one is the least element of set of natural number. Proposition is 1 is the least element of n. Proof. we have to prove that 1 is the least element of n. It is equivalent to prove that there is no integer between 0 and 1. It is equivalent to prove that. This integer between 0 and 1. This result will be proved by contradiction. This result will be proved by okay. We prove this result by using contradiction. What is contradiction? That is, we assume that 1 is not the least element of n. We have to prove that 1 is the least element of n, but we suppose that or assume that 1 is not a least element of set n, and by assuming 1 is not a least element of n, we will prove that 1 is the least element of n. Okay. This method is called the method of contradiction. Let it possible there be at least one integer between 0 and 1. Therefore, the set S is equal to set of element X belong to n such that 0 is less than X less than this is the set of such X which lies between 0 and 1, that is the integer which lies between our integer 0 and 1. Okay, we assume that we have such X since X is subset of n by way of principle. We have an integer L belong to X such that L belong to S and L is less equal X for all X in S. Okay. S as list element say L since L belong to S, rho less than L less than 1. Okay, because L is an list element, therefore L and L lies between set S, therefore 0 less than L less than 1. Okay. Multiplying the inequality out by L what we get? We get 0 into L less than L into L less than 1 into L, that is 0 less than L square less than L, that is 0 is less than L square is less than L and this is less than 1. Therefore, we get a number, such a number L less than L square is less than that number. Is this possible? No, this is not possible. Okay. This implies that L square is a positive integer between 0 and 1, but it is less than the list L, which is a contradiction. Because we take L is a list element, but we get another element which is a list element. This is a contradiction. Which is a contradiction. Therefore, our assumption that there is an integer between 0 and 1 is wrong. Hence, there is no integer between. Hence, there is therefore 1 is the least positive integer. Okay, here we have to show we show that 1 is the least element of set of natural number n. Corollary is the consequence of our proposition, that is it is obviously from our proposition that we have proved that if a is an integer, if small a is an integer, there is integer a and a plus 1. Okay. It's going to say that if a is an integer, then there is no integer between a and a plus 1. If we take a is 3, then 3 between 3 and 4 there is no integer. This is obvious. Therefore, there is no need to prove this corollary. Now we study an important property or a well-known property of scientist Archimedian, which is known as Archimedian property. Archimedian property or Archimedean property. This is an important property. We use this property by prove some theorem and solving some important problem. Therefore, this property is very important from view of learning algebra. So we concentrate on this property. We practice or write this property many times, then we remember this property. This property is useful in many theorems in by proving many theorems in algebra and linear algebra and also calculus. If A and B are any positive integers, then there exists a positive integer n small n such that this n into element A is greater or equal B. Okay, this property is known as Archimedian property. This property tells you if small a and small b are any positive integers, they both are integer, then there exists a positive integer other than a and b, which is say n, such that n into a is greater or equal b. Okay, then if you multiply this integer n to a, then this is greater or equal b. For example, if we take 2 and 3, here 2 is less than 3, and we take n is equal to 7, then a is equal to 3, then 7 into 2, which is equal to 4, is greater or equal than 3. This is n into a is greater than 3. This is known as Archimedian property. If you take any other number, that a and b, that is a is equal to say 7 and b is equal to 2. Here 7 is greater than 2, and we multiply this number by n is equal to 1 or any number. What to get? 14 is greater than 4. This is also true. If a is less than b, then also true. If a is greater than b, then this Archimedian property is also true. And a is equal to b, then this there is a symbol or what greater equal b. Therefore, this is also true for any inequality. Okay, equal or greater or less than. Okay. Then what is study in this Archimedian property? If a and b are any positive integers, then there exists a positive integer small n such that n into a is greater or equal b. This property looks very simple, but it is very important to prove many theorems of algebra and linear algebra and also calculus. So I conclude my lecture with this Archimedian property. In next lecture we study principle of finite induction. That is first finite induction theorem and second principle of finite induction. Also we prove some proposition, that is the well ordering principle in n implies the first principle of finite induction, and prove